Hello everybody. Uh, this is the first video about the chapter 3, the third part of our courses about doing the projects. Doing the projects is with different components, different input and output devices, and one of them that is one of the important ones is the 7-segment displays. 7-segment displays, first we need to know how they work, and then we will learn how to configure our program in the code vision AVR so that we can control this display. First I will show you what this 7-segment display is, and then how to connect it and how to configure it. I try to do as fast as possible so that you can if you need it, pause it. If you didn't if you just know what it is, you can just skip some parts. So 7-segment display is basically 8 LEDs. Here in the picture you can see this one is a 7-segment display. It has one pin as a common. It can be common anode and common cathode. Common anode means that the positive side of the LEDs the positive pin of LEDs are connected together. These 8 LEDs here are connected together, and the common will be connected to the 5 volt, and all the other pins will be connected to the 0 volt. In that case, all of the LEDs will turn on. And about the common cathode is that the common pin connects to the ground, and other pins connect to the 5 volt. This is like the LED's direction is reversing though. The 7-segment that we have is common anode. So here I will explain how to work with that. For controlling the 7-segment with a microcontroller, you need to set all of the pins that are connected to the 7-segment as output. So for example, here we will have this A through DP, all of these pins will be connected to one port A, I think, and this VCC is the common will be connected to port C. And if we give 5 volt to the port C pin and 0 volt to the port A pins, then this LEDs will turn on. If we give 5 volt to port C and 5 volt to the port A, they will not turn on, because there's if you give 5 volt or 0 volt to both of them, both of the sides of the LEDs, there's no potential difference, so it will not. There's no voltage difference on the input and output of the LEDs. So it means it will not turn on. In order to an LED to turn on, you need to have a potential difference. For example, if you put 20 volt on the plus side of the positive side of the LED and 15 on the other side, the LED will turn on. It doesn't have to be. It's not related to the 0 volt and 5 volt. If you have a potential difference between the pins of the LED and it's in correct direction, it will turn on. So here, in order to turn it on, we will put 5 volts here to the VCC, and then we will put 0 volts to the A, B, C other pins so that we can turn the LEDs on. How we show the numbers here. For example, we want to show number 1 here. Number 1 is shown like this. This one, the upper part, we don't need to write. We just put a 1 like that, and that's number 1. If you want to put number 0, for example, you have to turn on all surrounding, like the pins, the LEDs A, B, C, D, E, and F. So this number 0 will be shown here. You should turn off the G. This middle one should be turned off. But if you want to show 8 here, so you should connect the, you should turn on the 8 also. This is number 8. This is how we will show the numbers, and all the other numbers the same way. I don't explain more because I think you got the point. Here we don't have anything. This is a 1-digit 7 segment. We have 4-digit 7 segment, and 4-digit 7 segment is basically the same. Next picture will show here. This is a 4-digit 7 segment. It is the way that all of these A pins of all of them are connected together. They have just 3 extra pins, 3 VCC pins extra, and they are called here digit 1, digit 2, digit 3, digit 4. So this is the common pin plus pin, that for all of the LEDs that are in this first digit. This is the common end for the second digit, common end for third digit and fourth digit. This is how this is the 4-digit 7 segment works. For example, we will want to show this number here: 2 in the first digit, 3 in the second digit, 8 in the third digit, and 1 in the last digit. In order to do that, with the microcontroller, we can give 1 digit to only one of them at every time. But we want every LED to show different numbers. So we have a technique here that's called blinking, like 1 by 1. Blinking means that you turn on the first digit, and there you show number 2, for example, here. You turn it on for like 4 milliseconds, and then turn it off for 12 milliseconds. You turn this on, 4 milliseconds, turn it off. Go to the next digit, this digit number 2. There you show number 3, and for 4 milliseconds, and then turn it off. Go to the next digit, digit number 3, show number 8 there, and turn it off, and then go to the number 4, show number 1 there, and then do this cycle in every 16 milliseconds. You should blink these LEDs at least once. They have to turn on 4 milliseconds, then turn off 12 milliseconds, and during that 12 milliseconds, this is the other 3 digits are blinking, basically turning on and off. So by 16, it is here is the calculation. If we wanna, if one fact about our eyes that our eye, if some light is blinking, LED is blinking, if it is less than 50, our eyes can see it blinking. We can detect it. But if it is over 50, our eyes is not able to detect the blinking of that. So if we are blinking these LEDs with the frequency of 60, it means 60 times per second, our eyes will see them as always on. It will not recognize that they are being turned on and off. So in order to get the frequency of 60 Hertz, we let's see how long time we need to turn them on and off. So we divide 1000 milliseconds by 60. 60 is the frequency. Then we get the time period that we need to, during the 16 milliseconds, we need to turn each of the LEDs at least once. on and off, we have to turn it. So that means that for each digit, we have only 4 milliseconds to be on and 12 milliseconds to be off. So you see from where the 60 hertz is coming, why 4? If we make it less, also will be okay, because the frequency will be higher just. But if we make it more, for example, instead of 16 milliseconds, we make it like 32, the frequency will become 30. And then our eyes will detect that these are turning on and off. This will actually, it will disturb your eye when you are watching it. So that's the technique. That's how we will show a 4-digit in 4-digit 7-segment. Because we have only 2 ports for connecting to the like the positive side. We will connect this 4 ports, like the inputs, these to the port C, and these ones that are negative, these are the positive, and then these are the negative. These pins we will connect to the port A, these pins we will connect to the port C. And by turning them, by giving different voltage to them, we have to give 5 volt to the D1, D2, D3, and connect the A, B through the G. The DP is for this dot point, we don't use it. From A to G, if we connect to the ground, any of these pins that are connected to the 5 volt will be turned on, any of these LEDs. So I finish about the how to use the microcontroller. So let's go to code. How in our project. Let me see what is this project. That here. As you can see, we have a 4-digit 7-segment. The pin numbers you can see here. Here I made this circle here. These are the anodes that are going to be connected to the port C here. They have to have one current limiting resistor, also 1 kilo would be good. All the others, A, B, C, they are not in order. It's just because of practical reasons in the production of the LED, they had to make them this way. This was the comfortable way. So this is how you will connect. And all of these pins, we have to configure them as output. And so let's remember that when we are configuring in the code vision AVR, we have to configure these pins, 4 of them, and not the other 4s that are not used. Pins port C0 through 3 need to be output. Others, you should not put output, because if by any mistake, like in general, the pins that are not used, better to be input, not output. So that by accident you don't connect it to the ground or something else. Some big current goes and the microcontroller will burn because of that. So these are output. Let's go to the here. You have the 2 push buttons that you will connect to the pin B0 and pin B1, and you connect them to the ground. So when you are pressing the push buttons, they connect these pins to the ground and the value becomes 0. But if they are not pressed, the push buttons are not pressed, here should be the value of 1. So we have to pull them up internally. Or we could do it externally by putting a resistor here and connect it to the VCC. But we don't need it. We can do it internally. It's much easier. So this is about the schematic that we have to connect. Let me go to the code that we have. Why this is? Our task is that task as 4x7 segment is here. We should show a number in the 7 segment, 4-digit number, and by pressing two push buttons, we need to increase them or decrease them. And that is it. Here, like the comments in front of them, I hope they can help you to understand those. Char is the data type. Che is just the name. You could put any name here. And it has 10 items in it. 10 items of char type. Char is 8-bit data type. So, and our numbers are from 0 to 9. These are the 10 number characters. 0, 1, 2, 3 through 9. So those are the numbers. We will put them here. That's for that 0 to 9. That's for the digits. Yeah, the array of the 10 numbers is written. For the segment, segment is which LED, which LED number one, which digit. We had 4 digits there. Which digit need to be turned on? It's decided here. If you put 8, it is the binary value of 1, 0, 0, 0. So the most left is 1 and the other 3 are 0. So this will turn on the most left digit. It will give one value, like 5 volt, to the most left digit, and the others will be 0. So in every condition, only one of the pins is output and the other 3 are input. That's why if you turn them to binary, you will see the pattern. 0, 0, 0, 1. Here 0, 0, 1, 0, and then the 4 is 0, 1, 0, 0, and 8 is 1, 0, 0, 0. So in each time, in each of these selections, one of the port C outputs will be powered. Then the digits we have, the digits are for storing the number. For example, we have our number was what was our number there? Let me see. 2381. So we will have 2, 3, 8, and 1 in this digit. It has 4 integers in it, and they will be 2, 3, 8, 1. Yeah, here's the number. 2, 3, and 8, and 1 will be in this, for example, for the start. Integer ij, number, and temperature we are just defining so that we can use in our logic. The name, you could put anything you want. In the first solution, we have not used interrupt, so we will do all of the code inside the main code. So as you can see here, everything is like the way that is default. We have not activated any interrupt, any timer, anything. So all the code is here. Basically, up to here is not touched. But here you can see there is some list of the values for the character. Character is the same array that was supposed to store what LED combination need to be turned on in order to show the 0 number. And for 1, for example, what LED combinations need to be turned on in order to show the number 1. This is for the common cutout. So in common cutout here, the COM pin was connected to the ground. So here we had to go and give 5 volts. But we have common anode. common anodes or type. I commented them out, but they can be there just to compare. Let's watch here how it will show, for example, the number 0. If we want to show number 0, here we have to give 0 so that it can turn on. For 0, you need to give the first digit, second. Let me show for a second here. If you want to show the 0, it means A, B, C, D, E, F need to be turned on. The six LEDs need to be turned on. The G is the 7th digit. It need to be turned off. So we have to do that. The 6 digits are A, B, C, D, E, F. G is given 1 here, so it turns off. And for example, for the B, what LED combinations will give us a 1? It is that all of the 1s are turned off. Here A is turned off, B and C are turned on. B and C, that is 2. You can see here B and C. B and C. This will give us 1. Okay, I think it's clear here. I hope nobody has problem with that. In our code, first we have to let's take a second. In this one here, we have to you saw we had a number, for example, 4-digit number. We have to cut it to the single digits. So what was our big number that we had? Let me see. Okay, let's use another number. The example number was, for example, this one, 12.1204. If we are dividing it with the module operator, let me write it here. We write 1204. This is just an example. Do I have a modulo 10? Will give me this is modulo. I hope everybody learned this. Modulo will give me the first digit, the most right digit as answer. So this will be 4. The digit array 0, index 0 will equal with the 0. Then we will take the temperature equals the temperature. Temperature, it is temporary variable. It's short for the temporary. Then we will take the next. We will take 120 modulo 10, which will give us 0. The most right. The remainder basically of this division will be this. Then if you do these calculations, temp equals temp, like every time you divide this number, at first it was this number, then every time you divide it by 10 here, then here, then here, you will get here now 12 modulo 10, which will give us 2. But here digit is just 2. This 1, because digits 3, index 3 is equal with the temp itself, so it's just 1. So we will have digit will be the first index will be 4, second index first like zeroed index will be 4, first index will be 0, second index 2, third index. This is like 1204. This is how our number was. So let's finish that for a second. This is just for showing what it does. Here we will have incrementing the I. What is I doing? let's see, I is incrementing from 0 to 3. You can see if it is less than 3, this for loop will be done. So for I equals 0 till 3, I plus plus, increment I every time once. So at the beginning it will be I is 0. We will put port C equals with segment I. Segment I is 0. So segment dot 0, you remember segment dot 0 here was 8. And 8 means if you turn it to binary, the most left digit will be turned on. So I is 0. Port C will get the value that pin C dot 3 will be 5 volt, and pin C 0 and 1 and 2 will be 5 volts. It's like connecting 5 volt to the first digit of the 7 segment common. Okay, yeah. I is 0. Let's keep in mind this is I is 0. Here we have another loop inside this. We say that for J from 0 to 9, until J is less than 10, J until 9, J plus plus, do this loop. What is this doing? Say digits.I, digits is the here basically. This is updating the digits.I, is updating the value based on what is digits.I equal here. Here, for example, J is changing from 0 to 9, and if digits.I, for example, if I is 0, index is 0, I is 0, index of the I here was 0, so digits.I is 4. If J is 4, so if the J is 0, nothing happens. This is not equal, nothing is done here. J is 1, nothing happens. J is 2, nothing happens. J becomes 4, I is 0, this digits.I is 4, and when J is 4, port A will get J.4. So J is 4. This here we just transferring this value to the to this one. We take this configuration that the configuration of the outputs in pin port A. We take this and put it in port A. This is how we update the LEDs. We tell number 4 should be shown in the LED by putting this configuration, like port, this configuration. Putting this there, it will give us turn on the LED, the most left digit to show 4. Then let's say the I was 0, it finished. After that, J will just increase to 5, 6, 7. It will not be equal to this digits I. So here nothing will happen until I becomes 2. Here we have the for loop. I was 0. It put number 4 inside the first digit. Then I will be 1. I is 1. Segment that I at the port C will get segment dot I, and if you put the segment dot 1, you remember the number decimal was 2, and if you make it binary, it will be 0, 0, 1, and 0. It means port C will equal was 3. Sorry, this was 4. Sorry, yeah, 4. 0, 1, 0, 0. This will be port C dot 0 will be 0, C dot 1 will be 0, port C dot 2 will be 1, and port C dot 3 will be 0 also. So only the third digit or node will be connected to the 5 volts. It's a little, you need to just like sync and follow the I and J here, so that we have the second digit is connected to the 5 volt, and now we have to connect the port A to the negative side of the LEDs to like decide which number should be shown there. Again, we have here for J from 0 to 9, it will do the loop 10 times here and check if digits.I, when I is 1, digits.1 equals this number 0. If this number equals, at the beginning, the first like cycle, it will happen. J is 0. 0 equals 0. So port.A will get the J.0. And J.0, index 0 is this one. This combination will go to the port A. And this way, by increase, no, port A was here, sorry. We were here. Yeah, port A. And this way, this loop will just update the value of the port C will be on, and then port A will adapt to it, which LED configuration will show in each of the digits. And next part of the code is that here we will monitor if pin D.0 is pressed. This pin D.0 and pin D dot in the drawing, I remember it was a bit different. This is B, this is D. Okay, there's like we have to connect to the pin D1 and D0. There's no difference. Here, if we want to do this code, we have to connect them to, they should be D. D or B, doesn't matter, we can choose any of them. But here is D, so if we want to run this code, we have to connect those push buttons to the D.0 and D.1, which are D.0 and D.1 is this two. So we have to connect them here and here. Let's continue with that. If like we say, if port, if the push button, first push button is pressed, this line is added just for the safety. By giving 1 to all of the LEDs, we make sure that all of the LEDs turn off. What is turning off is in a nanosecond scale, that is not long time. Then we increase the number. Then we give a half second delay so that it doesn't. This can be less actually. This can be 50. It's too much here. 500 is too much. It can be 50. And this 50 is every time after pressing a push button. It's better in this application you can give a 50 millimeter delay so that it will not receive the bounce. During this 50 millimeter, the bouncing of the push button will be gone. So that's why we have. It should be 50. 500 is too much, but it will work. It doesn't make a problem. Just your pressing speed will be less. You cannot very quickly press the push button to increase the number very fast. Then the next line, if condition is that we say if pin D1 is pressed and the value of this number is bigger than 0, because we cannot show minus number in our 7 segment. We don't want the number to go to the minus. So we say if this number is bigger than 0, number minus minus, decrease the number. This is turning off the ports is just for the safety, so that all of the ports turn off, and then we change the number. This is the code. This is entire code. This code is written without using any interrupts. But we will do this. This I will explain in another short video how you use interrupts and make modular programming so that all of your code is not like piled up in only the main function. You see here the main function includes all of the code, and if there's a tiny error in the program, you cannot track. You have to follow entire parts. Modular programming means that you put in different functions, different sections, different tasks. So if you have, for example, a task that you want to separate the digits of the number from each other, this can be put in a function, and we will do that in the other the other code is done like that. Or in updating the LC the number for the updating the number for every digit on the display, on the 7-segment display also. Here is done during the main, and this will not work basically 100% correct, because all of the codes need to be run, then it reaches here. We don't have much control. We put delay for millisecond here, for example, but it's not exact. But if we use timer, we are sure that the timer does the interrupts after every nearly 4 millisecond. It would be much better to update, and we will get exactly 60 hertz there. Right now we don't know, because this is 4 millisecond, 4 millisecond. Why is the 4 millisecond? Is the time of every port must be turned on. Yeah, this 4 millisecond is for that every LED turns of 4 millisecond. But in reality, it's more than 4, because all of this code need to be executed also, and all of these 4 loops also need to be executed 4 times 10, 40 times. Here there's cycle being done. They are adding up to this time, and if our code is longer, if we have, for example, 1,000 line of codes, it means 1,000 millisecond or 1,000 microseconds. If we have 1 megahertz clock cycle, 1,000 microsecond or 1 millisecond also will be added. This 4 millisecond will be 5 millisecond. But okay, let's not go to the details here. This is the entire code, and now I will go to the code vision. Let me turn on the code vision, and I will show how to set up this. Yeah, code vision AVR is here. In this one. Now I just want to show you how to create the program and configure the pins and the interrupt and everything that we need in the code vision AVR. There it's pretty easy to do that. I will just explain how you can set up the timer and adjust the time for it, so that you can get 4 millisecond period for every interrupt to happen. Okay, let's make a new project. It asks, do you want to use Code Wizard? Yes, we will use the Code Wizard. This is what we're gonna do. It's gonna, yeah, this the window came. here. First you like always, first thing you choose is your microchip. What it should be, Omega 32A is for us. Here you can see always the 8 megahertz is selected. This is very important. So if you are working with the timers, first make sure that you select the frequency for your CPU that you want. Then you go to timer, because if you are, for example, here, you go to the timer and set your frequency here, for example, for let's say a 1 megahertz. Then later you come and on your chip change your like, let's change it to 4 here. Then let's go see what will be in the counter. 1 megahertz became half because it is following the chip. It is working with the frequency from chip. So if you should first set in here the frequency of the like system frequency, system clock. You need to set this. After that, you go here and check your clock. First it was timer 0 stopped. This is when we don't use timer. If we want to use timer, we come here and we have to select which timer we want to use. So we say we want to use timer 0. And here you can see timer value, compare value. We want to activate the overflow interrupt. We want to use this overflow. In this case, we need to, instead of timer 0 stopped, choose which frequency we need our timer to have. This is basically selecting the prescaler, so that if your if your system clock is producing 8 megahertz pulses, then your timer doesn't count with every pulse. It counts with, for example, if you use prescaler 2, it counts with every 2 pulse of it counts with every 2 pulse of the microcontroller on the CPU, only 1 clock for the timer. If you put, like, for example, 256 to be the prescaler, then with every 256 pulse from the CPU, the timer will collect only 1. It will count only 1 step forward. So let's see what is this menu that we have here. We have a menu for the timer 0. It's a 8-bit timer. So it counts from top is 0.0xFF. It counts from 0. Always it starts from 0, counts and reaches to the 0FF or 255. We can select here a value, prescaler value. For example, if you use 8 megahertz, it means there's no prescale. And in this case, it will take 0.0032 milliseconds or 32 microseconds for the counter to count 255 pulses. But if you use it, if you increase the prescaler or decrease the timer value, this clock value of the timer, then let's put this one. We can see that now it's already 8 milliseconds. The time for the timer to count from 0 to 255 will be 8 milliseconds. If you choose, for example, 7.18, this is equal. If you put the prescaler to be 1024, then with every 1024 pulse from CPU, the timer will count only 1. So when 8 megahertz is count by the CPU, the timer will count only 7813 pulses. it will take for it 32.768 millisecond to count from 0 to 255. So this is how it works. We want to have, as you remember, we want to have 4 milliseconds for every interrupt. So let's try to get this number to this 4 milliseconds. Let me put, for example, this 125 kilohertz. In that time, this time period for the timer is 2 milliseconds. The 2 milliseconds is less than 4, so we don't want this. It's okay if we use that, it will work, but we want to adjust to the 4. So I want to show how you do that. Then we choose the higher prescaler value. So we use the lower frequency of the clock value. If we use this, it means it takes 8 milliseconds for the counter to count from 0 to 255. Now we can manipulate here this 8 to be less. We can tell to the timer here that instead of counting from 0 to 255, count from, for example, 129 to 255. And that is here with giving the number to here. But here you have to give with the hex format. So like here 129, it is basically 7E in hex. Hexadecimal form of the 129 is 7E. If you put 7E here for the timer value, look, we got this 4.16 milliseconds. If we want to be closer to the like 4.16, we can tell instead of 129, count from 130. For example, instead of E, I will tell it F and see that the timer went less. It was 4.16, now it's 4.12. And so the more I increase here this number, I bring the start value higher and closer to 255. So it's less pulses that it needs to count. And according to that, this time is adjusted. Let's say this is okay. Our timer is overflow interrupt is set. This is here, we don't have to do anything anymore. And let's go to the ports. In the ports, as you remember, we had port A, Port A is the output need to be connected to the LEDs, and the port C, pins 0, 1, 2, and 3 is output need to be connected to the ports, to the LED anode pins. So let's continue with that. Port A, all of the pins are output except the last pin. This one we don't touch because it is the dot. We don't connect it even. And the port B, we had 2 pins according to that connection that we had here. The port B, they are push buttons. They need to be input and pulled up. Port C, the first 4 pins are output. These are output. The rest of them need to be input. In general, when we are not using the pins, we should leave them as the default that they are as input. Because if you leave them as output and by accident you connect it to the ground by mistake during the work process, a huge current will pass through the microcontroller and it will damage the microcontroller. That's why we are trying to it's safer to just have this as input if you are not using. So we got it. 4 pins from port C are output, are connecting to the anode pins of the 4-digit 7 segment. Port B, 0 and 1 are pull up. They are connected to push buttons. And port A is 7 beginning bits are output. So I think everything is done. Timer, I check again. We have 4.12 millisecond. And remember this 7F that we are entering here, it will be included in the code. So let's say program, generate, save, and exit. Let me make in the desktop a folder. Let's create a folder. Project 7 segment. Let's say, okay, open it. Then say 7 seg. Yeah, put here. Oh, the ports was here. That's okay. You know what I was just doing in the other window for a second. But you just input the numbers, and then this is the file that is made. Let me just go over this file for a second, what we just did. We activated the interrupt, as you saw, and the 7F, you remember, it comes here basically. It says anytime that the interrupt is happening, every 4 milliseconds, you come and reset the counter value to this value, 130. This is 130 in decimal. So start counting from 130 to 255 instead of from 0 to. So this is how it works. And then it says place your code here. The code that you want to you want it to be done every 4 seconds, you can add here, and we will update the number of the digit 7 segment 4 digits, every digit in every 4 milliseconds. So that is this. Let's see, the outputs, port A, they are set to the output. This is the data direction. Then port A, all of them are 0. At the beginning, they are turned off. Port B, they are all inputs, but the first 2 are pulled up. Port C, 4 first pins are output, the others are input, and all of them are turned off at the beginning. Port D, we didn't use, everything is 0. By default, they are 0. And then timer, in the timer 0 initialization is that we have clock value set for 31.250 kilohertz. This is the number that we selected there from the menu. The top value for the timer is FF, means 255. The output compare for the timer is disabled. The timer period right now is 4.128 milliseconds. And these are how we get to this configuration through this register. Timer counter control register for the timer 0 is this. And every bit here means something. Like by setting these 3 bits are for prescaler basically. This one, you remember 7F. We are setting that here. At the beginning, we set the count value of the timer to be 7F. And later, we continue that there also. In every interrupt, we update it. Timer 1 is not used, so everything is off. Timer 2 the same, we have not used it, everything is off. We have a register for controlling the timer, like configuring the timer in general, all the timers together. So here we are activating a timer overflow interrupt enabled for timer 0. So this one has turned to 1 because we activated the interrupt for it. And interrupt, or external interrupts are all off. We are not using the USART. All of them are the default 0, turned off. ACS, analog compare initialization, is on here. We could turn this off also, would be no problem. ACDC initialization, you can see everything is off. Yeah. Serial peripheral interface also we are not using, so it's off, disabled. Two-wire initialization is also disabled. This one is important, this line of code. This enables the interrupt, global interrupt. Anytime we want to use any interrupt, we have to use this one. So, and the next thing is the while loop. We can write our while loop inside our while loop or main code. And the thing that we want to be update the digitals, the update of the digital digits in the digits of 7 segment are done here. For 7 segments, each of them in 4 milliseconds need to be turned on and off. So that's why we will use the timer for that. And that's it, all that we needed. The code you can write with this basically. This is without the push button. This is, you see, with PBs, but without interrupts. You can see the differences that with what I just made. But here is with the interrupt and the function. Everything is here as I configured for it. Maybe port the connection of the push buttons was to the port D. But it doesn't change anything. It's just instead of port D, here I put port B. You can change the settings if you want. Okay, thanks for the watching. Thank you.